Hello, hello. Hi. Who do we have? Let me know when you can see and hear me, please. Hi. Happy Friday. Hello. Is anyone there? Is anyone there? Hi, James. Hi, Chinwendu. Yay. Amazing. Who else do we have? Hi, Bertha. Yay. Oh my gosh, I'm excited for this one. I mean, I'm excited for all of them. I need to stop saying that. Reminder, anybody that is watching on TikTok, if you actually want to contribute and ask any questions, then go to the link in my bio so that you can come over to the YouTube stream, which is where I am. Okay. Should we just get started? And then anybody that joins, so my hair is doing its own thing today. Okay, go away. Okay. And then anyone that joins can just join. So we're going to do some structure determination. We're going to do a 9 mark question. So one of those where they give you a whole bunch of information and then you have to use those to figure out the structure of an organic compound. Hi, Yashi. Oh my gosh, this lesson is going to be crazy for you, Yashi. So bear that in mind, but you'll learn something. So that will be fun. Okay. So before we get into that question, let's just do a quick reminder of what some of the key spectroscopic techniques that we use can tell us. Okay, so we'll start with infrared. Infrared, well, you tell me, what does infrared tell us? What information can we get from infrared? What do we get? What do we get? Oh, lovely. Hi, natural scientist. Yay, glad that you're here. I'm well. How are you? So we get wave absorption. Sure, all of those fancy physicsy words, whatever, what does it tell us as chemists that are trying to figure out the structure of an organic compound? What does it tell us that is important, that is going to be useful to us? What's it going to tell us? What do we care about? We care about these, so not necessarily the groups, although you're on the right track to Chinwendu. It tells us about the bonds that are present. Okay, it can sometimes also tell us like the functional group within which that bond lives. Okay, but ultimately it tells us the bonds. Because let's say if we look over here to this C, actually I wouldn't even say carbonyl, the C double bond O absorbance, we will see this peak whether we've got an aldehyde, a ketone, or a carboxylic acid, or an amide, or an acyl chloride, etc., etc. So it's not necessarily going to tell us the functional group, but it will tell us the bonds that are present. Okay. If we then wanted to confirm the functional group, then we could do chemical tests, for example. Okay. Now, there are, in my opinion, three, not even opinion, in my experience, three main peaks that you're going to see over and over and over and over and over again in your chemistry A level that you should be able to recognize with no context. So as soon as you see an infrared spectrum, if it's one of these three bonds, you go, I know exactly what it is. Okay, what that bond is, not what the compound is. So the first one, I'm going to use my highlighter to show you the three that are the key ones. So this purple one here, which is for your OH alcohol. So that's this smooth curve around the 3,000-ish range, 3,230, 3,550. Those values will be given to you in your data booklet. Okay. The other peak that's really important that you recognize is the other, oh, it's shifted a bit. This OH label should go over here. Okay, so we have the other OH peak, which is when we have a carboxylic acid. So it's shifted a little bit more to the right and it's broader as well. So it's a lot more jaggedy version of the OH peak. And then the third peak that we need to recognize, which is the one that I highlighted at the beginning, is the carbonyl peak, C double bond O. Okay. Again, you'll see this sharp peak. So it's really long and sharp. around 1,700. And as soon as you see that, you go, wonderful, I know that there's a CO double bond there. The transmittance, so ultimately, oh gosh, these bonds are absorbing infrared radiation to different intensities, essentially. Okay, which is why some of your peaks are a lot kind of more distinct, right? Much longer than others. In terms of like the mechanism behind infrared spectroscopy, we're not going to go into that today. Okay, the key is here, how do we use infrared to tell us about the organic compound that we have? Okay, so that's IR for now. The main three peaks that we're going to see, that we're going to use over and over again. We should be able to spot that with no context. Okay, the other peaks, they would usually give you some sort of hint within the question that that's what you're looking for, because it's a lot harder to spot this carbon-carbon double bond. Okay, so within the question, they might give you hints around, ooh, this reacts with bromine water, or there was an elimination reaction, and then you can use that information to kind of give you a heads up for what you're looking for. But the three peaks that I've highlighted, you should be able to spot with no context. Good question, natural scientists. So we will look at, so hang on, what am I trying to say? Radio is used for NMR, okay? But our next one is mass spectrometry. Now, mass spec, as I will shorten it, can tell us a bunch of information, but the most important one, the most important value that you're going to get from your mass spec for organic chemistry is your peak that is the furthest to the right. Because that peak is your molecular ion peak. And what does the molecular ion peak tell us? Chinwendu, sorry, to answer your question before, the fingerprint region, oh wait, let me go back, not molecular ion P, let me go back just for a second, okay? The fingerprint region, Chinwendu, is going to be over here, okay? So below 1,500, that's where you'll find the fingerprint region. So you can't actually, without having a bunch of spectra to hand, the fingerprint region isn't going to tell you anything. Okay, the fingerprint region is useful if you've got two compounds that have got exactly the same bonds. Okay, Aman, I do teach GCSE chemistry as a part of my course, so my Headspace course. And if you do want some revision on GCSE chemistry, make sure that you've signed up to the Easter revision course if you would like some extra revision over the holidays. Okay, so let's come back here. The molecular ion peak. What does the molecular ion peak tell us? What information can we get from the molecular ion peak? Not sure? Okay, it tells us the MR. Okay, lovely, Victor. Great. Yeah, Yashi, because it's when an electron has been removed, lovely, or a proton has been added, depends. But ultimately, the peak that's furthest to the right tells us the MR. So that's the one that's going to be typically the most useful. So this compound has got an MR of 72. Okay. Now we're going to use both of those alongside some NMR to figure out the structure of a compound. This isn't a full NMR lesson, so we're going to work our way through the NMR when we get there. Okay, so this is the question. Oh gosh, I'm in the way. No, I'm in the way of my NMR table. I'm going to have to float. Go up here. Okay, so we are told that compound H has an empirical formula C10H12O. The molecular ion peak has an MZ value of 148. There are 8 peaks in the carbon-13 NMR spectrum. The proton NMR peak at 3.6 ppm would usually be found at 2.6 ppm. And we are given two more pieces of information. We're given the infrared spectrum, which is this here, And we're given the proton, oh, I didn't label this, that's embarrassing. The proton NMR table. Okay, so what was gathered from the proton NMR spectrum. Hi, Fahim. Hi, hi. Oh, so let's take this question one bit at a time. Hi, Sean, indeed, because this is 9 marks. Okay, lots of students that are not you, okay, would look at these questions and go, oh my goodness, how am I going to get to the final structure? Now, the key is just have, do any of you watch Catchphrase by any chance? Because that's my approach to these questions. The catchphrase for catchphrase is say what you see. Okay, so you can get a number of marks, lovely Victor, you can get a number of marks in these structure determination questions just from stating what might feel like the obvious, but really you're doing some quite deep analysis of the information. So just state what the information is telling you, and gradually that might build you up to the final structure and you get all 9 marks, or it might get you most of the way there and you don't know how to put them together, and then you still get, 6 or 7 marks. Okay. Um, Not quite. So wave number is more frequency-esque. So because it's centimeters to the -1, whereas wavelength would be measured in meters. Okay, Fahim, this is some year 13 organic chemistry. Hopefully this is making you want to do A-level chemistry and not scaring you away. Okay, so let's do one bit at a time. Okay, we'll start with the simplest information. Again, we'll just start from the top. We're told that compound H has an empirical formula C10H12O and the molecular ion peak has an MZ value of 148. How do we use these two values to tell us the molecular formula? Well, yeah, the molecular formula, we know that the molecular ion peak with the MZ value, this tells us the MR. So we're given the empirical formula, and the empirical formula is the simplest whole number ratio. So the empirical formula is not necessarily the same as your molecular formula, but you can use these two pieces of information together to tell you what the molecular formula is. To do that, what we do is we find the MR of the empirical formula, and then we can compare that to the MR of the actual compound. So the MR of the empirical formula, we've got 10 carbons, so 10 times 12. We've got 12 hydrogens, 12 times 1, and then we've got 1 oxygen, so 16. What's that? 120 plus 12 plus 16 is 148. Wonderful. The MR of the empirical formula is the same as the MR of the molecular formula, which means that the molecular formula is the same as the empirical formula exactly. C10, H12. Oh, that's one job done. That's what? A mark? Calculating the MR and just seeing that it's the same. Okay. Ooh, so Yashi, if it was different, it wouldn't be a big number in the front. We would have to multiply everything by that number, right? So if we found that the MR for the molecular formula was twice as much, then instead it would be C20H24O2 because it's the same, it's just the same. Okay. So calculating MR of the empirical formula, seeing it's the same as the molecular formula, nice and straightforward. Sorry, let me go back to my spot. I feel weird up here. Let's go back. Okay. Now, our next step, and typically I would recommend looking at the infrared next. So leave the NMR till last. The NMR is what's going to actually give you the structure itself. It's the most kind of useful piece of information that you've got. But the infrared can start you off with making sure you've got the right groups. Now, the group that is going to jump out at us that we can identify without any context is, what do we spot immediately? Hopefully you can spot it. What do we have here? Which of our 3 bonds that I've said we must look out for? Not OH. OH would be over here like that. So there's no OH. What do we have? It's this one, which is our C double bond O. Lovely, Yashi. Great. Yeah. So how would we get the mark? By interpreting our infrared with the C double bond O, we would say that there is a hang on. What would we say? Woo woo indeed, Yashi. We would say peak, and then we would just say between, and then we would state the range directly from our data sheet, 1680 to 1750 wave numbers indicates absolutely C double bond O. That's it. We got a couple of marks already. Pretty good going. And we haven't done that much. We haven't done that much. Indeed, Chinwendu. Now we're going to get into the interesting bit. Like, I mean, I know it's been interesting the whole time, but when we get to the NMR, that's when we can actually start to build our structure. Okay. Now, let me just rewrite the formula up here at the top. What was it? C10H12O. Now, before we even get into it, there's something that we should notice from the molecular formula, which is there aren't that many hydrogens compared to carbons, right? 10 carbons with just 12 hydrogens, that is not going to be a straight chain, right? Or even a branch chain, because there's no way that we're going to get 10 carbons in a row. I can't even count, but let's say how many? 1, 2, 3, 4, 5, 6. Is that 10? I don't know. But then with only 12 hydrogens, that would just be one hydrogen per with a couple of them with two. So that few hydrogens is indicating that we've got some double bonds. And the number one group that we really should look out for is a benzene ring. Okay, that will become even clearer when we get to our NMR and when we see this here as our undefined splitting pattern. Okay. Yeah, so we're going to have a benzene ring because benzene, we don't worry about splitting for benzene. And we don't have enough hydrogens for it to not be that. Okay, indeed. So let's start to use our Proton NMR. Our Proton NMR, we would literally go one peak at a time, and then we'll figure out what each peak tells us about a part of the structure. Okay, now before we get into it, let's make sure we know what these three pieces of information tell us. So the chemical shift, that tells us the environment. Undefined, hi Gareth. Undefined just means that for A-level chemistry, we don't worry about benzene splitting because benzene does its own weird and wonderful thing. Okay, so I've kept it as undefined because we don't need to worry about splitting of benzene. Okay, so the chemical shift tells us the environment, and that's going to come directly from our data up here. So the type of proton, that's basically the same as saying the environment of that proton. Okay, the splitting pattern, what does the splitting pattern tell us? What does the splitting pattern tell us? Oh, wait, maybe I'll write it on the end. Environment. Let's do it here. That makes more sense. Splitting pattern tells us the number of protons on the adjacent, lovely Victor, on the adjacent carbon using our n+1 rule. And then the relative intensity tells us the ratio of protons on each carbon, or sorry, in each environment, not on each carbon. Okay, now the first thing that we should spot from our relative intensities is that they're not whole numbers. So that doesn't make sense, right? We can't have 1.2 hydrogens in one environment, 0.8 hydrogens in another. So what must we do to figure out how many protons, how many hydrogens are in each environment? What could we do? Oh, we could times by 10, but I think that would give us too many hydrogens. If we times everything by 10, that would give us 12 over here, then 8, then 8, then 16, then 4, but we've only got 12 hydrogens in total to deal with. So what could we do instead? Not even by 5. Oh, is it by 5? Not necessarily. We can divide them all, just like we do with empirical formula, right? Divide them all by the smallest. The smallest here is 0.4, and then we'll see if that gives us a whole number ratio. So if we divide 1.2 by 0.4, we get 3. 0.8 by 0.4, we get 2, and then 2, and then 4, and then 1. And then to see if that agrees, we then check that against the number of protons, the number of hydrogens in our molecular formula. So 3 plus 2, 5, 7, 11, 12, well, that matches. If it didn't match, let's say it only gave us 6, then we'd know we would have to double everything. Or if it gave us too many, then we would have to half everything. Okay, but if we divide by the smallest, just like empirical formula, then that will actually tell us our ratio. So we've got 3 protons in one environment, then 2 in another, then 2 in another, then 4 in another, then 1 in another. Okay. Any questions so far before we start getting into the nitty-gritty of each of these peaks in turn? Are we happy with what each piece of information is going to tell us before we start putting that into practice? Lovely. Okay. So let's take each peak at a time. So we'll say that our first peak, so that's the one that's at delta shift 1.2 ppm. Now I like to go up, okay? As in, I like to look at the ratio first, so the intensity, then the splitting pattern, and then the chemical shift, because that allows us to build a really nice full picture of what's going on in that part of the molecule. So for our first peak, the one that's at chemical shift 1.2, we've got 3 protons in that environment, which suggests that it must be a CH3. Yes, it is ppm, and parts per million. Why it's parts per million, again, that's a story that, to be fair, we'll get into in our actual year 13 lesson. But for now, those are just the units for NMR. Okay, so 3 protons in that environment, that suggests we've got a CH3. The triplet, that tells us the number of protons on the adjacent carbon. So because it's a triplet, how many protons, how many hydrogens are on this carbon next door? Oh, not 3. We use an n plus 1 rule. So triplet is equal to n plus 1. Therefore, n must be, lovely Gareth, 2. So we've got 2 adjacent protons. Hi, Ahmad. Hello, hello. Now we'll look at our chemical shift. The chemical shift is 1.2. Looking over our data, 1.2 corresponds with just kind of your standard alkyl groups, right? So just CH3s and CH2s. This is year 13, Elijah. Hi. So this is most likely it. Okay, so we're done with peak number 1. Thank you very much. Goodbye. Let's go to the next one. Okay. Let's go to our next peak with our chemical shift of 2.6 ppm. We have got, again, working our way up, 2 protons in that environment. Okay, I'm underlining the ones that are corresponding to this peak so that they don't get confused with the adjacent ones. Okay, so I'm underlining the ones that we're actually analyzing. Quartet means how many protons, how many hydrogens are on the carbon next door. Lovely, Chinaza. Hello, hi. 3, wonderful. Great. So already we're starting to see these 2 protons that we're analyzing from our second peak are probably the same as the ones that are attached to the CH3 in our first peak. Okay, we can't be 100% sure yet until we analyze the rest of the molecule, but we're starting to see how things are going together. Okay, and then the 2.6 range, what does that tell us? What does that tell us? Not very much, really, at this point. Yeah, I'm not sure how informative that is. Let's go to our next peak. Oopsie daisy. Whoa. Oh no. Is PowerPoint trying to rebel against me? Whoa. Okay, it's back. That was scary. Carbonyl. It could be. The only problem is a carbonyl, there aren't enough position spaces left on this carbon. What do you mean, like a C and then a double bond O? Potentially, potentially. But then that would likely end our molecule. Let's go to our other peaks and then see how it then would come together. Okay, so let's go to chemical shift 3.6. We have got 2 protons in that environment, so CH2. And then it's a doublet, which means that it's adjacent to a carbon with just how many hydrogens on it? How many? Lovely Chinwendu, just 1. So that's already telling us that these two, this CH2 is not the same as the previous CH2, right? Otherwise, there would be more splitting going on, okay? Oh, not necessarily Chinwendu, because if we look at the environment, we see the chemical shift is 3.6, but would usually be found in 2.6. So that actually corresponds to this splitting over here, right? 2.6, where the H is on a carbon that's next to a carbon with a carbonyl on it. Okay. It wouldn't match a C double bond because that would be in the 4.5 to 6 range. Ooh, that's a good question. Gareth, I think that's a typo. I think that's a typo. I think I need to go back to this data book and double check one more time because you're absolutely right. That doesn't make any kind of sense. Okay, let's go next to our 7.1 ppm. Now, depending on your exam board, you may or may not have the information for these protons. They're not here for AQA, but if you're OCR or EdXL, they actually do give you this information that these are aromatic protons. Again, if we didn't know that, we could still deduce that by how many carbons and how many hydrogens we have left over, and based on our overall molecular formula and the fact that the splitting, we don't have any splitting information. So these are going to be aromatic protons. We don't necessarily know where they're going to be yet, but we'll use later information to figure that out. And now our last peak at 9.7, what does that correspond to based on what we're seeing here? What must that be? So we've got 1 proton in that environment. Lovely Sahib, which is an aldehyde proton. Oh, hang on. That looks a bit funky. This is a triplet. So let me underline this one. How many protons are on the carbon next door? Lovely. 2. And so that's starting to look again like something we've seen before, right? That suggests that these two, the CH2 that's attached to an aldehyde, that must be the same as this CH2 that's attached to the aldehyde, right? So now we've actually got kind of a whole structure. Oh, hang on, let me clear some space. Close your eyes. Oh my gosh, close your eyes, don't look. Spoiler, spoiler. Oh no. Okay. Oh no. Oh my gosh. Okay, here we go. So we know essentially at this point that we've got a benzene ring. Attached to that benzene ring, we've got a CH2CH3 attached somewhere, and we've got a CH2 with a aldehyde attached somewhere else. Okay, and we know that because we've only got 4 aromatic protons, which means that 2 of the positions on the benzene ring have got our 2 branches on them. So this is going to be one branch on our benzene ring, and then this is going to be the other branch on our benzene ring. Okay, but now the question is, where do we put them? Right? Which positions on our benzene ring, how many times can I say benzene ring, will get our branches? Do we put them here and here? Do we put them here and here? Or do we put them here and here? What will answer that question for us? What's the last piece of information that we haven't used yet? What information have we not used yet? Just one thing. It's on the top of the page. Thank you, Sahib. The carbon 13 NMR, we have not used this information yet. So that's going to tell us where those 2 branches are going to be positioned based on the number of environments. Okay. Now, from our 2 individual branches, those are giving us 1, 2, 3, 4 carbon environments already. Okay, which means that aside from these 4 carbon environments from our branches, there must be 4 different environments. Hang on, can I count? Yeah, there must be 4 different environments on our benzene ring. So where does that leave? Where does that position our groups? Let's place them and see which one we get. Let's say if we put CH2, CH3 over here, and then CH2, CHO over here. Let's put it in the other 2 positions. Oops, oh my gosh. CH2, CH3, CH2, CHO, and then CH2, CH3, CH2, CHO. Okay, oh gosh, I'm in the way again. Which one gives us 8 peaks? Which one gives us 8 peaks? Let's count. Okay, in our first one, we'll have 1 environment, 2 environments, 3 environment, right? And then this is another one, 4, 5. Oh my gosh, there's so many. 6, 7. And then these 2 are different to each other as well. 8, 9, 10. So, eliminated. Okay. Let's go to our next one and count our environments, paying attention to they have to be complete, it has to be completely symmetrical for them to be equivalent. Okay, so even though, for example, these 2 carbons are both just CH carbons, they're different distances away from each branch, so they're not the same as each other. One is next to the carbon with the CH2, CH3, the other is next to the carbon with the CH2CHO, so they're not the same as each other. Okay, so let's look at the next one. Environment 1, 2, 3, 4, 5, oh gosh, 5, 6. And then again, these are not the same as each other. 7, 8, because they're next to different groups. 9, 10. Okay, so we know what our answer is, but let's check anyway. Okay, for our last option, 1, 2, 3. Let's go down here, 4, 5. And then because we've got a plane of symmetry, we've got symmetry down the middle, that means that these two carbons have got the same environment, 6 and 6. Okay, that also means that these two have got the same environment, 7, 7, and then 8. Yay. Great. Okay, that last part, probably the trickiest to get. You would still get, again, most of the marks if you realize that it's two branches on a benzene ring, but you put those two branches in the wrong positions. Okay, because using the 8 peaks in the carbon-13 NMR, that's the last kind of piece of the puzzle. Okay. Notice though, again, even if you didn't get all the way to the structure bit, you would still get a good number of marks. Let's go back to the beginning quickly and see where we've got our marks from. We have figured out the molecular formula based on the empirical formula and the mass spec. We figured out a key bond that's going to be within our structure from the infrared. We've analyzed 5 different peaks. That's 7. And then the last 2 marks, putting it all together. Okay, so again, using the information, building up these fragments, even if you don't know how those fragments come together, it's still a good chunk of marks. So similar to when I'm talking about calculations and I'm saying when in doubt, find the moles, similar to these, when in doubt, say what you see, piece together each individual part, and then if you can put them together, then fantastic. Indice and Rendu, environment is just what's around the bond. Do we need to know the formula for TMS? Yes, Sahib, we do. I'm going to go back here to put TMS. So TMS is tetramethyl silane. So it's basically a silicon atom with 4 methyl groups around it. It would be tetrahedral, but I'm drawing it flat just to show you what it looks like. Okay, so you've got 12 protons in the same environment, and they're all going to be downshifted, one strong peak, and then by definition, oh, I don't have the spectrum, they'll be at 0. Okay. Okay. How do we find that? Fun, exciting, best possible way to spend a Friday evening? Why is it used as the standard? Because you get one strong peak, Sahib, that is significantly, oh, hang on, upfield or downfield? Oh my gosh, I never get these right the same way. Okay, but one significant peak that's far enough away from all of your other peaks. And it's also easy to remove from your sample at the end. And it's unreactive, all of those reasons. Okay, good luck, Victor. Good luck. Don't forget, approach it methodically, one piece of information at a time. And then again, I recommend intensity, then splitting, then chemical shift to build up the different sections of your structure. Okay. Have a wonderful weekend. Anyone that is in my MES classes, I'll see you next week. If you're not in my MES classes, why not? Make sure that if you are interested, if you go to the link in this video, the description, then you can find out more about the main courses and also our Easter revision courses as well for year 13 and for year 11. Intensive courses over the Easter break to cover the entire spec for Maths, English, and the sciences. Okay, but for now, bye. I feel so small. Bye. Bye. Yes, indeed, Yashi. Okay. Bye, everyone. Bye, bye, bye.